This is the second lecture of the session. Here we are going to discuss about the electrodynamics of superconductivity and BCS theory. Electrodynamics of superconductors, which is commonly known as London equation. London theory is based on the idea of two-fluid model, according to which a superconductor can be thought to be composed of both normal and superfluid electrons. At 0 Kelvin, the superconductor consists of only superfluid electrons. As temperature increases, the number of normal electrons also increases. So, at any temperature, if n is the number of electrons per unit volume, then n is equal to Nn plus Ns, where Nn represents the normal electron and Ns represents the superfluid electron. If J is the current density, then J equal to Jn plus Js equal to ENNVn plus ENSVs, where Vn represents the velocity of normal electron and Vs represents the velocity of superconducting electrons. If a constant electric field is applied, the equation of motion of superconductor can be written as, that is, m into dvs by dt equal to EE, where EE represents the force experienced by a charged particle. Then the rate of change of supercurrent density is given by Ns E into dvs by dt. From this equation, we can substitute for dvs by dt in equation 4, which is equal to E by m. Therefore, equation 4 becomes Js dot equal to Ns E square E by m. This is termed as first London equation. If E equal to 0 in this equation, we get Js dot equal to 0, that is Js is a constant. Hence, no electric field is necessary to have a steady current inside a superconductor. First London equation explains the zero resistance property of a superconductor. According to Maxwell's equation, B dot is equal to minus curl E equal to mu 0 curl H dot, and curl H is equal to Js plus D dot, where Js is the supercurrent density and D is the displacement current. Thus, curl B is equal to mu 0 Js plus D dot. For a superconductor, the displacement current is negligible. So, we can rewrite this equation as B dot equal to minus curl E and curl B is equal to mu 0 Js. Substituting for E from the first London equation, we get B dot is equal to minus m ns E square curl Js dot. Using equation 8, we can substitute for Js, which is equal to curl B by mu 0. On substituting, we get B dot equal to minus m mu 0 ns E square curl B dot. If we substitute alpha equal to m by mu 0 ns E square, we get B dot equal to minus alpha curl B dot. Curl B dot can be expanded as grad div B dot minus del square B. According to Maxwell's equation, div B is equal to 0. So this term becomes 0. Thus equation 11 becomes B dot equal to alpha del square B or del square B equal to B dot by alpha. This is a second order differential equation having a solution Bx dot equal to Ba dot e raised to minus x by root alpha, where Bx is the value of flux density at a distance x inside the superconductor and Ba is value outside. In order to explain Meissner effect, not only B dot but B must be equal to 0. So the previous equation for B dot can be rewritten for B also. Thus, del square B is equal to B by alpha, having a solution Bx equal to B alpha e raised to minus x by root alpha. This is called second London equation, which explains the Meissner effect of superconductors. Thus, equation 5 and 14, that is first and second London equation, together describes the electrodynamics of superconductor. First London equation explains the zero resistance property, and the second London equation explains Meissner effect shown by a superconductor. We can find London penetration depth lambda from this equation 14 as lambda equal to root m by mu 0 ns e square. We are going to learn about the fundamental theory of superconductors, the BCS theory. This theory was put forward by Bardeen, Cooper and Schrieffer. This theory gained a huge success as it could explain all phenomena related to superconductors. The main feature of BCS theory was the idea of Cooper pairs. Cooper pairs are loosely bound pair of electrons with equal and opposite spin and momenta formed by electron-phonon interaction. In this figure, you can see two electrons of equal and opposite spin and momenta which are related to each other through a phonon. This forms a Cooper pair. Normally, two electrons repel each other. At transition temperatures, the electron-phonon interaction is greater than electron-electron repulsion. When an electron interacts with a lattice, it gets distorted. This distortion or lattice phonon shields this electron from other electrons in the lattice, creating an area of greater positive charge density. The second electron, which is at a distance, sees this greater positive charge density and gets attracted. Thus, electron-phonon interaction takes place. This results in the formation of a Cooper pair. This Cooper pair can move through the lattice without any resistance and exchange of energy. This explains the zero resistance property of a superconductor. Due to the formation of Cooper pairs, an energy gap is created in the spectrum of electron. This energy gap divides the Fermi energy into two, that is EF minus half delta zero and EF plus half delta zero. At zero temperature, this energy gap is given by the expression where omega d is the Debye frequency, V dash is the strength of electron-phonon interaction, and G of EF is the density of states. Conclusions from BCS theory are: Cooper pairs are formed only if the energy is of order h cross omega d. It is found that omega d is proportional to m raised to minus half, where m is the mass of superconductor. This explains isotopic effect. London equation can also be derived from BCS theory, which explains the zero resistance and Meissner effect shown by superconductors. Transition temperature calculated from BCS theory is Tc equal to 1.14 theta d e raised to minus 1 by V dash G of EF, where V dash is the strength of electron-phonon interaction, G of EF is the density of states at Fermi level, theta d is the Debye temperature. Thus, BCS theory could explain all the features of a superconductor successfully. Hope you understood the topics. Thank you.